Okay, I'm recording this after, so if you're listening at home, here we go. Let's see. So, okay, the idea is parametric equations which can be used to model movement. This is going to be pretty cool, and it's really cool at school, but we'll do our best here. So, a couple skills. First thing you need to be able to do is, given the equations, show the movement. That's the easier part. The harder part is from the movement, get the equations. If, in this case, I have two parametric equations, you can see that instead of a y-x equation, x and y both relate back to time. So I'm going to find horizontal position at times and vertical position at times and graph the movement by charting the horizontal and vertical positions at times that'll help me get a total picture. So in this case, if I go by ones for a while, I think that'll get me. Plugging in 0 into the x equation, I get 0 plus cosine of 0, which is 1. 1 plus cosine of pi over 2, which is 1. 2 plus cosine of pi, which is 2, minus 1, which is 1. That's weird. 3 plus cosine of 3 pi over 2 is 3 plus 0, which is 3. And 4 plus cosine of 2 pi is 4 plus 1, which is 5. And 5 plus cosine of 5 pi over 2 is 5. That is a little surprising, I gotta say. It's not quite what I expected, but we'll see how it goes. Let me make sure I didn't make any mistakes. 1 plus cosine of pi over 2 is 1. 1 plus cosine, is 1. 2 plus cosine pi is 2 minus 1. That is 1. 3 plus 3 by 0, so that's 3. 4 plus 2 pi is cosine, that is 1. 5, it looks good. All right. Now for y. At 0, 0. Sine of 0 is 0. Minus 0 is 0. At 1, sine of pi over 2 is 1. Minus 1 is 0. Sine of pi over 2 is 1. Minus 1 is 0. At 2, sine of 2 pi over 2 is sine of pi, which is 0. Minus 2 is negative 2. 3, sine of 3 pi over 2 is negative 1. Minus 3 is negative 4. At 4, sine of 4 pi over 2 is 0. Minus 4 is negative 4. At 5, sine of 5 pi over 2 is negative 1. Nope, that's 1. Sorry. 5 pi over 2 is 1. Minus 5 is negative 4. All right. This is going to be a little funky graph. We'll see. I'll put these together. The first point at time 0 is 1, 0. Now between, it looks like it did not move over the first second, but it actually did, and I can find how it moved in between, but I'll just wing it and go with the calculator, and we'll see. We'll check it with the calculator and fill in the dots. Right now I'm just kind of getting general points. At 1 second, then it's right back at that point. At 2 seconds, it's at 1, negative 2. At 3 seconds, it's at 3, negative 4. At 4 seconds, 5, negative 4. And again at 5, negative 4. All right. So the question is, what's going on in between? Now we could, like I said, take points, and I'm betting that it's not just going straight there or staying there. It's actually doing a little movement and then coming back to that point, which makes sense if it's a sinusoid. So get out your calculator and check, and we will see what's going on. In the graphing screen, go to the graphing screen and change your mode to graph entry, type parametric, and type in your equations. Change your t window from 0 to 2 pi to more like 0 to 4 pi so you get a more complete picture. Or even 0 to 5. We went to 5. This will be a little better picture here. All right, so if you graph that, you should actually get a little bit of a curly Q. I don't know if you can see my graphing screen if it's showing the smartboard, but I will sketch this and verify what you get on your calculator. It actually looks something like this. Now, in parametric equations, you always show direction of movement because it is supposed to model movements. So you do that with an interior arrow by saying the particle moved this way. You need at least one. You could do more if you like, but always have one on the inside, not at the edge. Check that, and if you are doing fine with your calculator, then we'll move on. The next idea is, instead of being given equations, you get the equations. This is the fun part. All right, this blows me away. So I often, when I'm walking down the hall, I walk down the red diamonds down the hall in a zigzaggy kind of fashion. It blows my mind that I could actually write equations that model that movement, that could make that happen in a kind of animation style in our calculator, you'll see. Now, when you go to make a model from a movement, you typically do this in 4 stages. You first draw a picture of the movement so you have something to look at and to communicate to the people where your origin is and things like that. So in this case, I think in class they timed themselves in 6th period, and somebody took 38 seconds to walk down the hall in that zigzag fashion. Now the hall is actually diamonds, and there are 11 of them before you get to the auditorium. It's 1-foot tiles in the hall, and there are 6 to the right and 6 to the left, and 12 every diamond. Now, we walked right first, or the person leading walked right first. So she went this way, and this way, and this way, and this way, through the end, and ended there. Now, in terms of points, I'm going to call my origin the point in front of my room. So here's my room, here's the hall, and she walked this way up the hall. So we want to write equations for that. Now, we need to get some points to look at. I can't write a trend to the horizontal position and a trend to the vertical position until I have some important points and when they happen. So let's start with the starting point. Time 0, we're calling this x0, y0. We're calling that point the origin. All right. We also know that she took 38 seconds to get here. Now let's call this the x and the y, or let's find the x and y here. As far as horizontally, that point is right in line with the middle. So it is neither right nor left or the middle, it is 0. But vertically, obviously, it's way high from where we started. It is 12 squares per diamond, and there were 11 diamonds. So that's 132 feet down the hall. Now, we need to fill in more details. It would be great if we could get down to a smaller scale. For example, these points. We really want to find out one full cycle of movement. So this now is what we need to write movement for. Let's start here. If I divide 38 seconds into 11 pieces, then she gets through a diamond in 38/11 seconds. That would mean that she gets to this zigzaggy point or halfway through a diamond everywhere she makes a turn at half of that, or 19/11 seconds. So really, in essence, the stars of the show, the quarter points are every 19/11 seconds. 19/11, 38/11, 57/11ths and 76/11ths. I think with those, I will be able to write the pattern to the movement. So, after you get a feel for points and times, then you make a table of those important points and times. Now, we're really going to do this twice. One connecting time to where it is horizontally, and one vertically. Time 0, x was 0. Time 19/11ths, x was positive 6 because we went right 6 of the origin. Then 38/11ths where we were back to 0. 57/11ths where we were left 6. And then 76/11ths we were back to 0. If I were to plot those movements then, time is the independent variable, x is the dependent variable, which is weird to see that on the vertical axis, but it is what it is. Then if I plot those 5 points, I'll start to see a trend. 0, 0, 19/11ths 6, 38/11ths 0, 57/11ths negative 6, and 76/11ths 0. Altogether then, the trend to the x movement looks like that. That should look familiar. You should be able to write the equation to that. It is x, I'm going with sine, the amplitude of which is 6, and remember the period, or the coefficient rather, is 2 pi over the period. So in this case, it's 2 pi over the period of one wave here is 76/11ths. T, I guess a cleaner version would be 6 sine of 11 pi over 38 t. Now do that same process for y. Feel free to pause the video while you try the y, and we'll check your answer. Okay, so here we go. Here are the points of y at time 0, 19/11ths, 38/11ths. I think that's all you're going to need because you're going to see a pretty easy trend going on. Y doesn't go back and forth. It continuously grows. You're constantly moving up. There's no up and down. So it's not sinusoidal. After the first time frame, you've gone up 6 tiles. Sorry, at time 0 you're at 0, but after the first time frame 6 tiles, then 6 more tiles, and so it is linear. If you were to look at that at time 19/11ths, 6, and so on. So as far as the slope, the rise is what, 6 over the run is 19/11ths t, so you could say that y is 66/19ths t. If you were to then graph that in your calculator, changing your window to an x of maybe negative, whatever, 6 to 6, if you want to go edge to edge, or negative 10 to 10 is fine, and y from 0 to 132, graph it, and then if you go to trace, so graph trace, and go right, you'll trace up the hall and you'll see yourself moving back and forth up the hall, and it's pretty darn cool, I gotta say. All right, so now you try. The idea is that you model movement by picturing the movement, identifying your variables, and finding important points in the picture. You make a table of important points, graph the important points, and write an equation to those important points that models where you're at different times, horizontally and vertically. When you put those together, horizontal and vertical position, you get a total position in 2 dimensions over time, which is parametric equations. Try this Ferris wheel problem here. Pause it for a second and try it yourself, and then I'll go over the solution. Okay, so if you have a Ferris wheel, and I believe it said that we're going to let the origin be the center ground point. So that's here. There's a 12-meter radius, and it says it's moving clockwise. Of course, every Ferris wheel really moves clockwise or counterclockwise, just depending on which side you view it from. So in this case, we're viewing it from the side where it's moving clockwise, this way. All right. Now, it takes, let's say we are the last person loading, so they're starting the ride when we're at the bottom times 0, and it takes 28 seconds to make a revolution, which means we are also going to be back there at 28 seconds. If this is the origin, then at that point we'll call this x equals 0 and y equals 0. As far as important points, you would also probably want to know those. Now, if it takes a full cycle in 28 seconds, then it takes a half cycle in 14 seconds and a quarter cycle in 7 seconds. So those are the important times. The x's and y's are negative 12, 0, and 12 for the x's, and 12, 24, and 12 for the y's. With those important parts, you could, some people skip the table and go straight to the graph, and that's fine. I'll show the table. The x time relationship is 0, 7, 14, 21, 28, and the x's are 0, negative 12, 0, 12, 0. The graph of that relationship then would look something like this. And it would be something like boom, 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 boom. Okay, so the equation for that seems like it is x equals a negative sinusoid with an amplitude of 12, negative 12 sine. The period is 28, so the coefficient is 2 pi over 28, or pi over 14 t. Always verify your equation works by plugging in a point or two. I think you'll see that that equation works. Let's go y. At time and y 0, 7, 14, 21, 28. The y's are 0, 12, 24, 12, 0. That's going to be a little different. It looks more like that. That is a shifted center line up at 12, so it's more like y equals 12 minus 12 cosine of pi t over 14. That then is the model. Together they should show, when put together, a person going around and around on a Ferris wheel. Use your calculator to prove that. Moving on to the next skill. All right, so it's sometimes the case that you want to graph the movement a little more quickly. I can graph these by making a table and figuring out the path, but it takes a while. It's much easier sometimes to graph the path if you have x and y related directly, and you eliminate the parameter of the time. I guess I should have started my notes with that. The parameter, which is like the word for a condition, is time. They're parametric equations because both horizontal and vertical position depends on the parameter of time. Sometimes you want to remove that parameter or take time out of it and relate x and y directly. That's called eliminating the parameter. There are two types of problems, either algebraic or trig. If you do this algebraically, you typically do it by substitution. But a warning, when you do this, you're trying to still make the same path of movement. And if the original parametric equations were restricted to a certain region, then you have to take steps to make your graph restricted to that same region when you get just x and y. I'll show you what I mean, but that's the hardest part, really. Here we go. So I have two equations, parametric equations, x equals 3 plus 2t and y equals t squared. When I want to eliminate the parameter, that means I want to take x or take t out of the mix and relate x to y directly. So if I were to solve this first equation for t. T is x minus 3 over 2. If I then put that into the y equation, y equals x minus 3 over 2 all squared. You could also say 1/4 times the quantity x minus 3 squared. It says sketch it, so I'm going to sketch this. This is a parabola shifted 3 to the right. And normally I would say this is a y parabola, looks like that. And I'd call it good. There's two problems though. First of all, I need to show the direction of movement. Second, I have a little bit of a problem, and that curve doesn't really all happen. First, the direction of movement. The x equation can give me the direction of movement. You can look at the x equation and see as time gets bigger, x would get bigger. Well, if x gets bigger with time, then it must be moving to the right, that way. So I know the direction of movement now. The restriction. Why is there a restriction at all? Well, you can see that time is restricted. And because time is restricted to only positive, that means x will be restricted. X won't be everything. I won't get all kinds of x's. If x is 3 plus 2t, and time is greater than or equal to 0, then x is greater than or equal to 3. Negative x's never happen. Likewise, y, if time is greater than or equal to 0, then y equals t squared. Well, that actually is going to be the same either way because it was squared, but y will be greater than or equal to 0. Those should be included with the equation to get the same movement. Now, the movement then is actually, or the path is actually just this. And if you want to erase that, you can, but it's only going from a starting point here in a half parabola fashion. All right, now that's algebraic. You substitute one into the other after solving for t. You never, never, never do that in trig equations. Here's why. Say look at this pair of equations, and you solve this one for t. You'd say t is x minus 3 divided by 2 and the inverse sine of that. Then if you put that into the other equation, you get y equals 2 plus the cosine of the inverse sine of x minus 3 all over 2, all that squared. Now that might be some fine thing to you, but it's a mess. And if you do that in your homework and you substitute, I am going to come back and say, all right, now you graph that. And good luck to graphing that. It's not very pretty. Instead, what you will do is use identities. You know that sine squared plus cosine squared is 1. So if you can just get sine squared and cosine squared, or even just sine and cosine, then you are golden. So you should try and make sine squared, make cosine squared, and then add the two equations. Now if I were to make sine squared from this first equation, I would want to move the 3, divide by 2, and square. And I would get that sine squared is x minus 3 over 2 all squared. The second equation already has a square. I just have to move the 2. So y cosine squared is y minus 2. Now if I add the two equations, the left side is sine squared plus cosine squared. I can replace all that t stuff with 1 then. That's what allows me to eliminate the parameter. On the right hand side rather, I get quantity of x minus 3 over 2 all squared plus y minus 2. If I were to put this in a little more friendly fashion, I might say leave y on that side. I'll move this side over and I'll call it negative 1/4 if I square the denominator. X minus 3 squared plus 3. That's not too bad. I can see that that is a parabola shifted right 3 and up 3 and opening down. Now the only question is, or the questions are direction of movement and restrictions. What about the direction of movement? Well, if x is tied to sine and sine goes big and small, then x will get big and small, big and small. So I feel like it's should go right and left and right and left. Same with y. Y should get big and small and big and small. So let's see just exactly what's going on here. Let's do the restrictions. I know that sine is between -1 and 1. Now, if sine is between -1 and 1, then x, as a consequence, would have to be between 3 minus 2, or 1, and 3 plus 2, or 5. So I'm not going to get this whole equation. I'm only going to get from 1 to 5. Let's take the y's to confirm. Cosine squared is between 0 and 1. Because of the square, it can't be negative. So it's strictly between 0 and 1, which means y, which is 2 plus that region, would be between 2 and 3. That seems to jive. These two things together means that we're just getting this curve back and forth. So the direction of movement, you could either put arrows going back and forth, either pointing out or pointing in, but either way, you should get arrows. That shouldn't go to the axis, by the way. It should stop at 1. But it looks something like that. All right, so that's eliminating the parameter with restrictions on the domain and range. Last skill is a calculus skill. The calculus of parametric equations, or at least a starting point, when you want the slopes to the tangent curve. Now, surely we can eliminate the parameter in some cases and get the y-x equation and do our normal calculus, but sometimes that's not feasible. Look at this problem. If you tried to eliminate the parameter so that you could then take dy dx, solving for t is no picnic. In fact, it's a nightmare. So we're left with wanting to keep t, but how do we find dy dx with t in the mix as an in-between? Well, as an in-between variable kind of reminds me of a chain rule approach. So I'm going to think of how I can do dy dt's and dx dt's together and get dy dx. Well, if it's a quotient, it would make sense to take the quotient of dy dt to dx dt. dy dt is 3t squared minus 1, and dx dt is negative t to the negative 2 minus 3e to the 2. They say at 4, so I'm going to evaluate that at time 4. That's another reason to keep it in t, because the time, or the condition at the point at which they wanted it was a time, not an x or a y. My answer is 17 over, let's see, that was like negative 1 over 16 minus 3e to the 4th. I'll call that good. That's pretty ugly. And that's it. Now, that should get you started. As far as the questions on the homework, we didn't have a lot of time at this point, so they turned it in. I'm just going to check it, and we'll go over it better tomorrow. Make sure it's done when you walk in tomorrow so I can check it before we start going over it. The idea being I didn't want a copy fest. I wanted to see that you at least tried them on your own. Have a nice night.